All right, somebody just. All right, Sam. Can you see what I'm doing? Okay. Really? Even I mean, okay. Now, theoretically, you can see what I'm doing, but you're seeing it on a phone. Is that good? I'm asking out of curiosity. Oh, what kind of phone you have? Huh? Okay. All right, so we have our RLC circuits, and I think sometimes people might think in this modern day and age they're not important because maybe you've heard, something like inductors are too big, or um, but what I'll tell you is, you know, sometimes I feel I've dedicated my teaching career to hunting down these things that everybody knows and everybody says and is like totally wrong, right? So when they say, "Oh, RLC isn't an important," um, the inductors are too big, right? That's what they'll tell you. But all I can say is you can go and buy a wide variety of inductors. If they were never used anymore, how is it that there's companies that can still sell them and be in business, right? So that's a baseline. Now, also, I can give you another. I won't really go into the details today, but you can have a microcontroller, right? And that's a digital device, right? But sometimes you take that digital signal and you want to convert it into an analog signal. And in fact, it seems to me one of the best ways is to use an RLC circuit. And I'm just giving you the heads up for 110 is that because we store energy two ways, right? So the capacitor, right, was like the bucket of water, and the inductor was just things moving around, right? Because of that, we can get, I'm going to, we can get complex roots and better filters. Now, don't let that throw you, right? That's, and yeah, just so you know, you probably need an op amp at the end of it. All right. But I needed one of these filters, and I went into it thinking it had to be some kind of op amp or RC based filter. And right there in the TI app note, they were using this circuit. And that's like a company trying to sell their microcontrollers. Now, it's not like a logical proof, maybe, but why would they steer you wrong? You'd only get mad at them and their microcontroller. So when you're mad and the filter's not working and you throw it across the room, you're throwing a TI microcontroller across the room. All right. Now, there's other things that are important too with RLC. And it has to do with that kind of energy storage. All right. So, if we have a mass and this is so long, right? And is it swinging back and forth, right? It goes between potential energy, right, where it's at the top, and at the bottom it's all kinetic energy, right, where it's moving. So we're storing energy by, even though it's moving, right, there's no friction, right? So it's not really doing any work. It's just storing the energy in movement, and then it comes up, and now it's storing it all in potential, back and forth forever. Well, really, that's what will go on. If I put some energy in this circuit, and maybe I have to give it a little kick, it will oscillate as the energy gets stored back and forth between the capacitor and the inductor. All right. Now, you might be thinking, this uses two kinds of energy. This stores it two different ways. Maybe they're the same. Well, just as a quick example, if I have an elevator, right, and this is a spring, and this is a damper, right? Now that's velocity. That's velocity, right? If I push up on this, well, the damper is like a resistor. The spring is like an inductor, which is really great because it kind of looks like an inductor, right? And then the mass is the capacitor. Now, you might think, and anyway, this becomes, I accidentally switched those, but because they're in series, it doesn't matter. So the LRC mass damper spring. Now, 1 Henry doesn't give you a spring constant. There's conversion in the numbers. But here's the thing. All of our analysis tools in EE98, and we can find the voltage division here, we can find the current, all relates to the physical system. So we can simulate this, right, which well, it's like a shock absorber on a car. Although the shock absorber on the car has these two in parallel. All right. So you can simulate things like that with you don't have to learn anything new, right? We have it's called the inverted pendulum, right? Some other people might call it a segue, right? This thing is going back and forth and we're trying to balance it, right? So we're going to learn all these analysis tools in 110 that can be applied to any mathematical system. Anything with differential equations that happen to be linear, you can actually use circuit analysis to solve them, all right? So it's super important. Now, with the first order, right, we really had we really just had e to the minus t. And it was either over RC or R divided by L. Now, whether there was a 1 in front of it, whether we're subtracting, but no matter what, it was always this, okay? With second order, and yes, I think I'm making a really funny joke. It's not. It's more complex because we're going to use complex numbers. Okay. Anyway, so the second order is more complex. And really, you can make a big deal out of it, but I find you just have to know the quadratic equation to figure out what's a system. Okay, as long as it's not me. Okay, so really we just need the quadratic equation to see how are these systems going to behave. And yeah, with the first order, we could come up really easily with something like this, right? Second order, it's a lot harder, okay? There's two energy storage elements, so you need more than one initial condition. And so you don't necessarily need the equation with what is this value, what is this value, what is R, what is C, but you want to know how is it going to behave, all right? And what are the big behaviors, right? We call the first one, our jargon is overdamped, right? The second one would be critically damped, right? Underdamped. Now, the thing about all of these I'm sorry, I'm going to use a fancy word here. They all converge to a finite number eventually. So if I put in a step voltage, and this is node 2, the overdamped system it's going to start rising, and then it's and it doesn't overshoot, right? But eventually it converges at, in this case, 1, right? The critically damped system has a slightly different curve, but it can be almost impossible to tell the difference, just to let you know. But it converges at a known value, right? The underdamped is pretty obvious, is that it goes up at least once, okay? And it can wiggle, but eventually it converges to a value. So the phrase is, these are all what you might call stable, all right? Now, yep, it might take a while to get where you're going, and this might oscillate, and it might take a long time to settle, but they're all stable. Unfortunately, there's, well, no, I'm just saying, there are some conditions that are unstable, and they're captured in those 101 problems, all right? But that we're going to go over, all right? But basically, the unstable, right, you might get, it just goes up exponentially, right? It might wiggle as it goes up exponentially, or you got a sine wave, right? It never converges, it just is a sine wave. And all of this you can kind of get from the quadratic equation. All right. So I think, you know, now, yeah, you can have a second order system with 2 capacitors or op amps and capacitors and things like that. And yeah, in 110L, I show an example of a 7th order filter. Okay. But it will all come down, and by order, second order 2 energy storage elements. There'll be a polynomial with an order of 2. But even if I had 7, right, that would really be a second order times a second order plus a first order. So if you want to understand first and second, well, you can just combine them any way you want, right? All right. Now maybe we want to actually solve something. And I'm all right. Now, with the first order, how did we do? We just said, well, I know it's going to be e to the minus t. Then you just have to remember, is it e to the minus t divided by RC or the inductor? And you kind of just looked at where it was going, and you could figure everything out. But with the second order, we kind of need to figure out what it will do. Takes more work. And so it's kind of better to just find the natural response first. And we're going to do something called find the roots. All right. And yep, you can do this all in differential equations. And on those first orders, right, it was kind of easy. You just did it in your head, right? You knew, oh, the mess equals the negative of the derivative of the mess. Oh, it's exponential decay. Well, just like I said up here, I'll just scroll back. All right. You can have over, critical, underdamped, and then there's 3 ways of being unstable as well. So that's like 6 possibilities just that I can think of off the top of my head. Whereas before it was exponential decay and that was the end of it, right? Now there's in 110 there'll be some more formal complete ways of doing this, but this seems to be the quickest way to get to the answer that I'm about to show you. So these are all in series. So I'm just going to draw a current. I'm going to call it capital I, right? And then I'm going to put in the voltage drops, right? Because, yeah, right here, the current is going from bottom to top, so the voltage drop is plus minus. Here it's going left to right, plus minus. Here it's going down, plus minus. Then so it's one mesh. The easiest way to solve it is mesh. There's 2 nodes you don't know, so that would be 2 nodal equations. So that's why I would do it with mesh. So VR plus VL plus VC. And now I'm going to do a trick. I'm going to say ZL equals SL and ZC equals 1 over SC. So here's my differential equation. I take, and it's all in terms of time. It's just too hard to write out. Or I take the Laplace transform of the derivative, and then I make everything capital. I, a function of S, V, a function of S, C, and then S. When you take the derivative of something, you just multiply it by S. Then I solve for Z, which is like resistance, right? V divided by R, I, and it's 1 over SC. Now, S has a real, an imaginary component, and you might right. This is how you find the Fourier transform, right? You multiply whatever function of time you have times this, integrate. And that's not today's lesson. I'm just trying to tell you is that S, we take something in time here and we turn it into S, and you should just know that That's the imaginary. That's the real. That now there's this two-dimensional plane here that time gets converted into frequency. And not only that, it's not just regular old frequency, it's a complex frequency where you have all this stuff going on here. So the thing is this S, right? If we find an S that's all real, it does one thing. If we find an S that's it's all imaginary, it does something else. If this is positive, it does one thing. If it's negative, it does another thing. And this is how we can get to the bottom of the thing is I can jump in and we can solve for S, use the quadratic equation. Great. But just so you know what it is that we're solving and really how insanely cool this is, something in time with an integral, and now we have complex and it's in frequency. That's just amazing. Sorry for that brief aside. I'm going to rewrite it again. VR plus VL plus VC equals 0. And notice, I can have the VL first, the VC second. I can move all of these back and forth. And what that's telling me is I can rearrange the circuit parts, and still the circuit's going to have this fundamental thing. All right, so I'm going to use capital I because it's the Fourier transform of it. So I times R plus I times SL plus I divided by S times C. That S, right, it's a complex number, equals 0. All right, let's collect the I's. Now here's an important part. If I of S is 0, then I of T is 0, and that means, here's T, and the current is just 0. It's boring. There's nothing to worry about. So if that's 0, let's just move on, right? So that being said, we can ignore it and just worry about the inside. R plus SL plus 1 over SC equals 0. Then solve for S. Now to make that happen, we need a to use a quadratic, and we need it in like a real polynomial format. So I want having this divided by S doesn't work. And then when I multiply this and get S squared times L, that'll make things a little harder. So I'm just going to multiply through by S, multiply through by L, And I'm going to get S RL plus S squared plus 1 over LC equals 0. And then I'm just going to rearrange it to something that is easy for me to see. All right. So roots, right? What are the roots of that equation? All right. Well, we use, minus b plus or minus and the thing is, a lot of times we can just see what's going on here. All right. But so b would be minus r divided by L, right? Plus or minus r divided by L squared minus 4. A is 1. C is 1 over LC. And this just becomes 2. All right. Well, if RL squared is greater than 4LC plus or minus So basically, this becomes a real number. It's plus or minus a real number. So I have a negative plus or minus something that'll be smaller than that. And so I get 2 roots here. All right. These 2 roots mean 2 exponential decays. All right. And so it's almost like a first order system where you just have e to the minus t, right? Because both of these are real, right? That's what you're going to get. Now, r divided by L squared equals 4 LC. You get minus RL plus or minus 0 divided by 2. 2 roots at R divided by L. So there's 2 roots here at the same place. So wherever it is, there's one, and I'm not quite sure. There's two there, right? It's just I don't know how to draw two over each other. Okay. Now that's going to have one. Everything's going to have exponential decay, right? But that's going to have this linear part in front of it. Okay. And again, I'm just kind of giving you the broad brushstrokes. Now, RL squared less than 4LC is going to be minus RL plus or minus now I'm just going to right? If this is bigger than that, it goes negative, and therefore I'm going to have plus or minus something with a J. The quadratic equation, right? Yeah. So what this means is it's got the same real part, but it's plus an imaginary part minus an imaginary part. So we had two real roots. And you know what? I think I'm going to redraw it down here. Imaginary, real. I have two real roots. Then, as they get closer and closer together, they become critically damped, right? And then as you get more and more, as that, or I guess what I'm saying is, keep 4LC constant, but keep this term going down. It'll start off overdamped, then it'll get to critically damped. Then if it keeps getting smaller, you get two complex poles. The complex pole thing, yep, that'll have e to the minus t, but it will also have some oscillation to it. All right. Now, if you have things over here, I can have two roots over here, But what I'm going to get is exponential increase. If I have it at the same spot, I'll have exponential increase. And here, then if I have complex, it'll oscillate exponential increase. And if I'm right here, I'll get a sine wave. All right. Which are the choices? Oh, these guys? All right. Yes, but not necessarily from an RLC circuit. All right. But here's the thing. If there's no R here, if R is 0, yep, it's going to oscillate. Now, there are little R's in here that, yeah, what if you calculated it out and 1 year from now it stops oscillating? Well, you could have superconductors, right, instead of resistors, and yeah, you could get that, right? Remember that inverted pendulum? You can get, the more it goes over, the more it wants to fall over. And the variable is the angle rather than, and so that physical system is over here, right? And then when you do circuits with negative feedback, oh yeah, you can get that. And having something right here is in fact the Laplace transform of an integration equals 1 over s, which puts 1 root right at 0, right? And yeah, so that's totally physically possible. Yep. Now, okay. Now there's something I just need to briefly go over before we do an example. All right. This is a parallel circuit. All right. And nodal analysis is the way to go. And you have I'm just going to we're going to go over this in more detail, but this has a different B term. So if you go and put in the constants for RL and C, and it comes up over under critical, it's not going to necessarily give you the same, like, if this circuit is overdamped, right? You take those same RLC inverted things and put it in here, it won't necessarily be overdamped. So you got to derive out the root equation the same. But still, if, so yeah, if, 1 over RC squared is that greater than, less than, or equal to 4 LC. That'll give you the same kind of conditions. All right. And it came out last semester that people thought they were the same circuit. You just did it. No, the same concept, but the way it's arranged has two different things. And there was a lot today, right? Yeah, normally I try to show you how to do the problem, but we're going to probably have to do that next week. All right. So in general, we just have to worry about, is this bigger than, equal to, or less than? All right. Now, something to consider. Notice this one is going to be, it's got a cosine, but that's exponential increase. This has exponential decay, right? And it'll go like that. This one has, this is the critical damped because it's got the T in exponential decay. This has two exponential decays. This is over. This, oh, and I should just say that's under. This doesn't really have a name, but let's just, in this case, if R equals 0. So if R equals 0, we have 0 plus or minus 0 minus 4 LC divided by 2. We get plus or minus J 4 LC divided by 2. That's two purely imaginary numbers. Those two purely imaginary numbers make it oscillate. Now, in the parallel case, it's different. All right. This one, I don't know, the positive constant, the numbers don't really come up that way. It's a distractor. So what you do, so up here it'll give you the numbers. You derive it out, come up with this. With the parallel case, right? It's this. If R is 0, then this goes to infinity. But if R is infinity, this goes to 0, and that's where you get that oscillation behavior. All right. And those do show up. But really, you come up with this relationship. Now, I'm just going to say, there's something where it's like, well, 2 alpha plus omega nano, whatever. I know in the 98 textbook, they start talking about all this business. It's way too much effort. Now, later on, we're going to use in 110, sometimes it's better to use certain terms. But, man, every time I see this and this on the exam, they're getting this wrong. Because I grade them by hand. All right. So I really feel that in this case, is it over, under, critical, or is it going to oscillate, right? Well, just solve it. an impedance way, right? Come up with this equation. Remember the quadratic equation. Imaginary numbers oscillate. That's what they do. Anyway, got time for a question or two. I'm not going to describe the 98 way because I don't want you to. What the 98 way, you would come up with a whole differential equation and then find the eigenvalues, and then it would make you convert, like 2 alpha would equal RL. Well, then you got to convert all that. Then this is actually not so bad. It's just 1 over LC. But why? Oh, and then, okay, when I said that's not so bad. But then it's 2 alpha minus 2 alpha, 2 alpha squared. What? I can't even remember it. I can remember the quadratic equation. I'm just saying, right? You used it in high school, right? It's so, you can't forget the quadratic equation by now. So why add to it? All right, now I'm starting to preach a little bit, but you know, we all have a lot to remember. My trick is keep it simple and then modify this thing that can't be forgotten, right? So I thought, well, first order, the mess equals the negative derivative of the mess. It's got to be exponential decay. Then I try to remember the RC, then that leads to the RL. This case, no, you need more, right? You kind of need to remember that the impedance is SL, 1 over SC. But you can remember that from physics. Then, but mesh analysis, you already remember that because if these were all resistances, you'd have no problem, right? Then we tie in imaginary numbers, or they're not imaginary, and so but yeah, you got to know the circuit analysis, you got to know the impedance, you got to know the quadratic equation, and then what these things mean, right? But every time you see cosine or sine, there's an imaginary number in there somewhere, right? 2 real roots, that's kind of easy because that's just 2 exponential decays. 1 root repeated, I don't have an easy way to remember it, but when you have a t times the exponential decay, that's just critically damped. Huh? Yeah, she did the differential equations method. All right. But which you might have done in differential equations. Sometimes they use the same RLC. But at the end of the day, you could have done the differential equations part, but you would still have the quadratic equation, and you would have this bit. And although they might call them eigenvalues, right? What the 98 textbook does is say, well, no, you got this. Now put it in terms of alpha and no, whatever. So if you felt more comfortable with differential equations, okay, but you're still going to have this. Now, what I'm saying is that RLC, parallel, and series are about the only thing you can do the differential equations way. It's going to get so much more complicated that you're going to need to do it the Laplace transform way. And when you design circuits, you design them in the Laplace transform space and then convert it like, all right, how does this look in time? So where we're headed as EE students and practitioners of the EE art is we're going to work in the frequency domain so much that you might forget these things really exist in time. Okay. Anything else? All right. Oh, I'm hopefully. Oh.